Saxon Algebra 1, Lesson 84. We've got a two-parter, gentlemen. John is just cheating and double-decking the topics on us. The first thing we're going to do is talk about multiplying radicals. All right, here is the cool thing about radicals. Radicals are this little sign. They behave very much like the three little pigs. Here's the deal. You know that in the story of the three little pigs, they went out to make their way in the world and they each built their own little house. I'm just talking about two little pigs here, right? I think straw and sticks, I think were the first two. The third guy with the bricks, he was the one who had it going on, right? But these are just the first two, and we're multiplying them together. Now, here's what's cool. If the pigs want, they can run, oops, I'm sorry, that should be an N. They can move in together and live in the same little pig house together. That's perfectly fine. And vice versa, if they're living together as they were at the beginning of the story and they want to split out to go and build their own places, they can do that too. We can move them back and forth from the same house to individual houses to the extent that it makes us happy. Huh, okay, good to know. We're going to practice multiplying them. And it's pleasantly easy. And we're going to add the character of the big bad wolf, because right up here we're just talking about pigs, right? Now, here we have a situation. Our letter pigs have turned into number pigs. That's fine. It's a 3 and a 2. But each of these pigs have a number on the outside. That is the wolf, the big bad wolf, if you don't mind me saying so. Numbers on the outside of a pig house are wolves. Numbers on the inside of a pig house are pigs. Radical signs are pig houses. Please don't go to college and say pig house. I mean, you can think it. I would be happy if you thought it. But that's a radical. That's what we call that sign. It's a radical sign, all right? So don't say pigs and wolves in college. I mean, you know, maybe. There's cool math teachers that would think that was fun. But here's the rule for multiplying radicals. We multiply wolf to wolf and pig to pig. I'll show you what I mean. That sounds weird, but you'll remember. Wolf to wolf is 12. Pig to pig is 6. There's our answer. What? It really works, you guys. This wolf to wolf, pig to pig thing is going to stand you very well. Let's do another one. They're going to get a weensy bit harder as we go. We have 4 of these to do, but it's not going to be horrible. That's the same. I'm squishing them together a little bit. Okay, we follow our same rule. Wolf to wolf is 24. Pig to pig, 18. However, we see that this is a pretty big number. Maybe we can break this down and take some of the pigs out. And my metaphor gets a little shaky here, but just follow the math with me. All right, let's try breaking this down into its prime factors. That is the way to simplify radicals, is rewrite them as their prime factors. And I'm going to go sideways. 18, I think of it as 2 times 9, and then 9 breaks down to 3 times 3. Okay? Every pair of pigs can jump out as a single pig. So, 2 pigs on the inside equals 1 pig on the outside. Now, I'm not sure how that relates to the story. And every metaphor breaks down sooner or later. But one pig on the inside is 2 on the outside. So here we have, or I'm sorry, I said that wrong. 2 on the inside equals 1 on the outside. Here we have a pair of pigs, so we can jump that pair out and we'll multiply the wolf times the new pig, which is 3. 1 on the outside, 2 on the inside, right? We have to have 2 in order to jump them out, and then they only count as 1. I hope I'm making sense. So now the 3's are gone. We still have the 2 left inside. This is 72, so our final answer is 72 times the square root of 2. That's correct. I was looking at a different problem that has a 72 in it, but not this, and I was like, how could I have possibly gotten that wrong? But then I looked up at the next one, and I was like, oh, never mind, I didn't. All right, so we do want to simplify radicals whenever we can. This will test your knowledge of perfect squares, right? Because if you realized, oh, 18 is 2 times 9 and 9 is a perfect square, that helps you. 6 is 2 times 3. There's no pairs of pigs in there. We got to have pairs to get anything out, right? Poor pigs. We make them jump out and face that wolf. But I mean, because I think that's how the metaphor works. I'm not sure, but that's why they have to jump out in 2s, is because if it's just one of them, the wolf would just eat them. But if there's 2 of them, then they stand a chance. But why they turn into just one, I'm not sure. I haven't developed that part of my thesis. All right, let's make it wee bit harder. Oh, wee like pig, right? 4 times the square root of 3. John's really big on that one. Okay, instead of just having 2 little bitty radicals, we're now doing a binomial of radicals and then multiplying it by another one on the outside. Okay, that's distribution. We can handle it. Ba-bump, ba-bump, right? Easy. So we follow our rule, wolf to wolf, pig to pig. My book's busy trying to fall. So this would be 20 times the square root of 6. And we make a mental note. Okay, 6 is not going to break down. And then plus, okay, 6 times 4 is 24. Here we have, I'll write it down, but I'm just going to write it as 3 times 3. I'm not going to write that as 9 because I would turn the 9 right back into 3 times 3. But there they are. They jumped in together, and now we can follow our 2 on the inside, 1 on the outside rule. Bring that one out, multiply it by 3. The radical's all used up. So the final answer here is 20 times the square root of 6 plus 3 times 24 is 72. And now you know why when I had this answer, but I looked at this answer in the book, I was like, what? That's not even close. But they both had the 72. Okay, beautiful, right? Kind of easy, kind of fun, kind of no big deal. One more, and then we will change to our second topic. 84.4. Simplify. It's another distribution one. What's weird or different about this one? This last number doesn't have a radical. And that just makes the ground wobble under our feet a little bit, right? What are we going to do with that? Well, let's start by doing everything in order the way we know. Wolf to wolf, pig to pig. 4 times 3 is 12. This is going to be, I'm not even going to multiply them because 2 times 2, that's 2 on the inside, 1 on the outside. So I write it like that, right? And then I can cross that out because it's all gone away. Okay, now let's do the second one. And it's plus in between, just like any distribution. We'd put that sign down there. Now, here's the thing. Is that a wolf or a pig? It's a wolf, right? Pigs are inside their little houses. If it's just a number chilling, then it must be a wolf. It's a wolf that hasn't got a pig house on his radar yet, right? He's just roaming around the forest looking for something to eat. So he's not chilling by a pig house yet. But we handle him just the same way. We'd multiply this and we would get 20 square root of 2. And so then just to fix this, this would be 24 plus 20 times the square root of 2. Final answer. Yay! I find multiplying radicals to be profoundly satisfying. The whole way it stands up to that 3 little pigs metaphor, I find purely satisfying. It's easy to remember what to do. We got some great little taglines. So if you can get those starting to jump into your brain, it'll be a piece of cake. All right, now I'll blow your mind a little bit. This is not hard. It's just vocabulary that makes everybody wince. We're going to talk about functions again. We've been talking about them a little bit on and off. I mean, honestly, I get confused because I teach 4 levels of math, Algebra 1/2, 1, 2, and then advanced. And everyone's talking about functions now and then, sprinkled in with their other lessons. But different people are at different places and learning different things, and so everything goes a little bit crazy to me. All right, a function to me is best understood as a machine. It's a machine where we take inputs and then we grind them through. This is our raw material, and this is our machine. And this is our output, what we make, right? Our product. Sometimes it helps to think of this as input and output. This, the fancy name, is function. All right, that'll make more sense to you in a minute. Now, the way this works is that our function machine has a little formula. That looks familiar. We've seen things like that all the time, right? No big deal. And when we use a function, what we do is we choose some raw material to put into the machine. Now, in this case, John has chosen for us, so we'll use his input. He chooses the numbers 2, 4, and 7. Of course, our raw materials are numbers. This is a math class, for crying out loud, right? We're not going to use ingots or something. What is an ingot? It's a chunk of metal, right? It could be gold. I don't even know. Okay, so what we do is we start with taking 2. We take 2 and we put it into our function machine. That means we solve it. 2 goes into the place of the x. 2 squared is 4. 4 plus 8 is 12. So I write it up here so that the 2 and the 12 are kind of by each other. Now let's take 4 and put that into our function machine. 4 squared is 16, plus 8 more is 24. And now 7, I mean, that number's getting a little bigger, but it's not exactly hard, is it? Oh, wait, did I do that wrong? Oh. My numbers are different than John, but that's because my function's different. It's fine. Just don't look in the book and expect them to be the same. 7 squared is 49, plus 8 is 57. So that's how a function works, right? We're given the function. Sometimes we get to choose the inputs. Sometimes John will give them to us. Sometimes real life will give them to us. But we just take them one at a time and we put them into this expression, which is something you've been doing in those evaluation problems, right? And then we get answers. And a function, technically, well, I mean, this is a function too, but a function means a mapping. It means that for every input, we have one output that goes with it. And we know that every time we put 2 into this function, we're going to get 12. Every single time. We're not going to get 47. We're going to always get 12. There's a 1-to-1 mapping. That's the best kind of function. We're going to learn some pickier things later. But for every item, there's one output that goes with it. Now, these groups of what we put in and what we get out have fancier names. And I hate to throw these names out, because at this point, most students are like, yeah, okay, this is not that big of a deal. I get it. I've seen problems like this. Sure, I see how we got these. Now I'm going to give these 2 things fancy names. This I'm going to call the domain. And this I'm going to call the range. Do not let those semi-weird words freak you out. Domain simply means the numbers we put into the machine. Range simply means the numbers we get out. Don't let it freak you out, okay? Now, another thing that we can do when we're talking about functions is if we don't want to draw this whole crazy picture, we can just write the input and the output as a pair, right? If we put in 2, we'll get 12. If we put in 4, we'll get 24. And if we put in 7, we'll get 57. That's easy, right? I didn't do anything fancy. I just took the input and the output and put them together. But this is super helpful. We call this X, and usually we call that Y, right? That's cool. That's really familiar. We could graph those if we wanted, right? And we could draw a picture and say that's the picture of this function. That's doable, and P.S. spoilers, we will be doing that in the future someday. But when we use function language, this is another thing. Don't let this blow your mind. Instead of calling it Y, we call it the f of X. What? What that means, we would name this also the f of X. That means X is the number we put in, and this is the number we got out of that function. And then I might have another function machine down here that I would call the g of X. This one I called f. That's kind of like the basic name that mathematicians always use, because f for function, clever, right? So for this particular function, I call these the f of X. We'll talk about that a little bit more. Just know that we do that instead of calling it y. It's no big deal. It doesn't mean anything all that special. Now, I want to go back to this whole idea of mapping. John wants to beat this into our heads really severely. Well, I mean, not severely. That would be painful. But he's going to drive this point home, all right? So he's drawing these pictures. What he's drawn here is the function inputs and outputs. He didn't draw the machine in the middle like I did, but this is the inputs, that's the outputs. Oh, look, he used domain and range. And he says, does this diagram designate a function? So what we do is we look at the inputs and we say every input should lead to one output. Remember how I drew the lines? Well, look, these work just fine, don't they? So yeah, that looks good. That looks like a function, right? Now, what about this one? Does this designate a function? All right, Y turns into P. Now, they're letters instead of numbers. We try not to let that mess with us. But yeah, this one has a partner. A goes to X, but what's going on with M? M has an arrow going to X and to 5. Remember how I said that was a deal breaker? We have to know that every time we put a specific value, letter or number, into the function, we have to get the same thing out. M is some kind of weird hybrid beast that sometimes gives us X and sometimes gives us 5. So that's not a function. Sorry. No. Now you see where I'm showing you the book and not drawing all these pictures. Okay, does this diagram designate a function? Now this one's a little tricky because we see the V-shaped thing and we start to go, oh, no, you don't. All right, in this case, A goes to 5. That's a one-on-one, right? 4 also goes to 5. Now, it's a little weird that they both have the same value, but we notice that they each only have one value, right? So that's okay. It has to be predictable. A will always give us 5. 4 will always give us 5. That's fine. What we can't have is this situation where the input leads to two different outputs. Two inputs can go to the same output, but we can't do it that way. So this is fine, and then 7 goes to 11. Yay, that one's good, right? All right, now what about this one? Does this diagram designate a function? Now, suddenly John's drawing a very different picture. This time what he's doing is he's putting the function, the machine part of it, back into the picture, right? Here we didn't see any machine drawn in the middle. And here, he didn't draw the rectangle like I did, but he just wrote the equation there. Huh, okay. And then he says the inputs are real numbers. All right, we know what real numbers are. They're like everything, right? Fractions, decimals, positives, negatives. So could we take any real number and put it through this function machine, which is adding 2 to it? Yeah, we could. That would be fine, right? So even though this looks really weird, we say, yes, this is fine. It says take the real numbers and add 2 to each one of them. And we know, okay, that's going to get you one answer for every single different number you put into it. So we're good. All right, now we're going from this style of picture to the ordered pairs. Okay, remember how I did that here? Here are the 2 circles, and then I switched and showed how the circles can be rewritten in this format. So now we have to take our brains and we re-squish them. And, well, I mean, that sounds painful. But what we recognize is that the first number in every pair is the input, and the second number in every pair is the output. And this shows how they're partnered. So what this means is that every first number should always go with the same second number if they repeat. Let's see what happens here. 4 goes with 6, that's fine. 7 goes with 2, that's fine. We don't know what the rule is of this function. We don't know how we're getting from one number to the other, just like here we didn't know. But that's not what we're worried about. We're worried about making sure that each input has only one output. But look what happens in this third one. 4 is now paired with 5. First we said 4 was with 6. Now we say 4 is with a 5. It's like when you get an Amber Alert on your phone, right? We're getting that terrible noise in our brains. Set A does not designate a function because 4 has 2 different images. That's another fancy word for related output. All right, now let's try it over here. 4 goes with 8, 15 goes with 6, 11 goes with 7. That looks fine. I don't see any drama there, right? And John agrees. Set B does designate a function. All right. Oh my gosh. John is going ape on this lesson, isn't he? We have 12. Which of the following sets of ordered pairs are functions? All right, so we're in the pairs again. Again, we're looking that if any number is repeated, if the first number of any pair is repeated with another pair, they have to have matching outputs, if you will. Okay, 1 and 2, 2 and 3, 3 and 4, 4 and 5. There's no repeats of the first number, are there? So that's fine. 4 and 3, 2 and 2, 4 and 3. Okay, 4 and 3 repeats, but it's exactly the same. And then 3 goes to 3 also, but that's okay. We don't know what the function is. Maybe that makes sense. But as far as we're concerned, that looks just fine. How about this one? 1 and 2, 2 and 3, 1 and 3. I already said 1. Drama, drama, drama. 1 and 2, 1 and 3. No. B is out of our list. 1 and negative 1. 4 and negative 1. Negative 1 and negative 1. 3 and 2. Okay, there's a lot of negative 1s in there, so let's go back and look. Are there pairs? Is there more than one pair that has a negative 1 in the first position? 1, 4, negative 1, 3. No, there are no repeats. So, which one was the loser? This one, B is the loser, right? Set A describes a function. Set B is not a function. C is a function. D is a function. Yay. Okay, so which one was the drama? B. Because 1 and 2, and then 1 and 3. All right. How about 11? 7 goes with 11. 6 goes with 4 or 8. No. 6 has 2 images, to use that word, right? Sometimes 6 is 4, sometimes 6 is 8. No, that's no bueno. Okay, how about this one? 6 goes to 4. 7 goes to 11. So far, I like it. 5. 5 has no one. It's not a function, okay? And it's not a relation. That's another word that we haven't really talked about yet, and I don't want to talk about it too much. Is John going to make us talk about it? A relation is a pairing that matches each element of one set with one or more members of another set. So this one could be considered a relationship because at least everybody has someone. But 5 is just alone and adrift. So this is not a function, and it's also not a relation. Okay? There, John says that. Okay, finally we come to the end of 84. Pictures, lots to look at. Remember that these diagrams and these lists of pairs are showing you the same thing just in a different way. That's why I showed it to you this way, so you could understand the relationship between pictures like this and lists of points like that. Okay, I hope it's all as clear as mud. This is just words and ideas, you guys. Don't let it freak you out. The numbers are easy. This, I hope you enjoyed. All right, I will see you soon on the video chats. I think that's all I have to say to you. Okay, goodbye.